All right, and then I'll be. Anybody who's seen me talk before, I have a rather informal style, which is a way of saying I don't over-prepare for things. So let's just see. It's actually quite efficient, because what we can do with a group of this size is, if we have an idea, we can take it and run with it and see where we get. I've got a list of topics that I want to make sure that I cover, so you get your money's worth from this session. But within that, we've got a fair amount of flexibility. And I'll be doing a lot of drawing on the flip chart and a bit of typing. So that's where we are. There is a memory stick here I'll pass around. Anyone that's got a computer, there's on this there's a workspace called Dfns Talk. You might want to copy onto your machine. Has anybody got a computer with them? You don't need to use your computer in, but it's effectively, it's just the map of what we talked about as a reminder. And there's a couple of examples that I'll be running through, but you don't need to have it if you. It's just called. There's just one workspace on it, and if you pass it around.
Oh, I don't. Here.
Yeah, I mean, if anybody's got it, pass it around. Otherwise, come and see it later. Otherwise, it'll be on the Dyalog website next week. So there's no rush if you don't want to do that. We're nearly through the introductions. The other thing that I've noticed in these sort of sessions is sometimes I've been in a session where I violently disagree with what the guy at the front is saying, but I've been a bit reticent about saying so because I thought it was impolite. I've got this is under the title Rules of Engagement. Can I urge you, if you disagree with something or you think, no, that's not my experience, if you're brave enough to share it with us, then we will all learn something from it. It's a really good thing to do. It takes a little while to pluck up the courage sometimes. It's not... sometimes it's a misunderstanding. Often when we're introduced... I think this is just a general truth. If somebody has a different take on the material, sometimes that different take or framing is really valuable. People sometimes invent a whole new paradigm because they've misunderstood the old paradigm, or they've come at it in a different way. So please, I sometimes will make assertions which you think, that's not right. So if you're brave enough, that's really good to challenge that. Right, and the final thing in this very sort of airy thing. Oh, can you hear me? Again, if you want me to repeat things, I know sometimes my British accent takes a little tuning into sometimes. So again, we've got plenty of time. We can just play around. One of the things I'd like to do is to introduce you to the functional programming paradigm. It sounds a big sort of heavy-duty piece of philosophy, but it's just a little trick in thinking, and it's quite strange. If you can get it, I'm not particularly good at it. It's almost like like a Zen thing that sometimes you can get into this zone and be thinking this way, and then you can fall off the wagon and you think in the old way. But what I'll try to do is to choose my language that I use to describe things, to promote this way of thinking about things. And what I'd urge you to do, what I've been, in your situation, sitting on the other side of the room, I'm awful. What I do is cling to the stuff I already know, and I think, no, I'm not going there. This is not the way. What we could do is to free our minds from now until the coffee break. What's the worst that can happen? Just let go of everything. It's not brainwashing, but it's a sort of rinsing with what I'd like to do with this stuff. So it will become clear. I'll explain the difference of attitude as I go along when I can. So if you can free yourself up. I guess everybody has written a program in a language, possibly in APL, so you have ways of thinking about things. Right, so that's the end of all of the nonsense. You're going to hear some Anglo-Saxon sometime during the morning if I stand up too quickly and bang my head. All right, so this is the first. This is really Zenny. Here's the first thing I want to show you. Let me just do this. +/b. This is the very best expression in APL. Divided by rho of b. Okay, and this is an expression for average, or the mean item of a vector v. And this is so important, this little expression, because if you were to write that in a language other than APL, maybe write it in C or in Java or whatever languages are out there, the way you would write that is to say, I guess you'd say 0 a total, go around a loop, umpteen times accumulating a total, and then divide by the number of items. And the beautiful thing about APL is that this is just a single expression, and there's very little to go wrong. You can't go round the loop too many times. You can't forget to initialize a variable. This is part of the beauty of APL, in that we can stay in the world of expressions. Is a very simple and regular world, and we can do all sorts of nice thinking about expressions. But as soon as we go out of the expression world and we go into a world where we're putting loops and go-tos, branches, and tests and things, we sacrifice something. And the functional programming paradigm helps us to stay in this very simple world for a lot longer. Yeah. I'm going to show this. So first of all, I'll tell you what. The other thing I'll do is I'll show you this is, again, you may choose to leave after you see this. What have I got here? I should also say there is a workspace called Dfns.dws that is supplied in the product. That'd be a good thing to write here. Dfns.dws is supplied in the product, and it's an accumulation of examples of programming in D functions that's been written over 10 years by a lot of people who have more time on their hands than is healthy, and they've naming no names. And people have produced little examples, so there's a wealth of examples here, and this can also be found at www.dialog.com/dfns, no dot. So if you go to that web address, then effectively what happens is people send little examples of programming in, and I'm the editor of this workspace. I just edit them into the workspace, and then I press a button and it generates HTML pages for each of the things in here and puts them on the website. So I'll be showing you a lot of examples from this workspace, and effectively this workspace is the course material for this morning's session. Okay, what was I going to? I lost my train of thought. DWS. Oh yeah, here's the reference code. Right, so here I'm using version 11. In version 12.1 we have a user commands, and somebody else will be talking about this. So effectively what this this user command is just a way of getting into a saved workspace, opening a window on something in a saved workspace. So it's not important, but what I'm doing is looking at something in the Dfns workspace, and this is a complete reference manual for Dfns. So it really isn't a very complex beast that we're dealing with, and so we'll be visiting each of those. But effectively, there's we've only got what is that 9 little sections to go into. So we'll come back. We'll come back to this one. Okay. Now let me really get down to brass tacks now. A Dfn is an expression involving alpha and omega and a bunch of other stuff enclosed in curly braces. Has everybody seen a Dfns? I don't know you probably know this. No. You haven't. Okay, that's good. So we'll start. That's great. Thank you. All right. So in APL we have arrays and functions and operators. That's all we have. Yeah. Shout if you disagree with this stuff. Am I speaking too quickly or?
Namespaces, classes, workspaces, files.
Okay. Yes, that's good. Okay. In our world of expressions, I should have said not in APL. That's good. Yeah. In our world of expressions, we have arrays, functions, and operators. And if I have an expression within curly braces, then that makes a function or an operator. And the way I refer to the arguments of this function are to have omega to represent the right argument and alpha to represent the left argument. So to write our little mean function, I could say +/omega divide by rho omega. And this is a fully paid up Dfn. I can't really rev this font up anymore. Can you see that? Yeah. So this thing, including the curly braces, is a function, and so it can be used in any context that we can use a function in APL. So I can apply it to. I could apply it to an array. John, yeah.
Following one of your first admonitions, I urge to stop and object a moment ago with your question or your comment. I like to think of APL in two senses. First, it's a mathematical notation, or notation.
Yeah.
Secondly, necessarily, the word is used for a deliberate environment of that notation.
Yes.
I think you feel somewhat the way I do about APL primarily to us means.
Yes.
A very carefully worked out, concise notation.
Yes. And in fact, that's I agree. And one of the ways of looking at Dfns is that we have this nice regular world of expressions, and then to be of any use to us, we have to package them somehow to make functions. And we have what I call traditional functions, which is like APL 360, where you have a header line and you have labels and branches and control structures. It's one way of packaging expressions into something else. And Dfns is just a different packaging for expressions. Yeah? Okay. So this is a function, and
not just. It's also a subset of the current delivery of the other way of packaging.
The
other way of packaging expressions. In other words, they can be included within the other paradigm, or the other means.
Yes, we can mix and match them to a certain extent. Yes, the packages. So a function within I call them Dfns, the Dfns and Dfns. The traditional function with its header line, I can call a Dfn, and a Dfn can call a traditional function. So they're just two different paradigms. One of the things I will say is that when you see this stuff, it is so simple. You think, well, but for any real work, we would need to use Dfns. And that may be true. You may feel comfortable about that, but it is formally, mathematically possible to write any computable program using just this stuff. And there are some other surprising claims that we can make as we go along. So I'm going to hit enter on this. So what we have here, as I said, this is just a function. So in APL, if I apply a function to an array, the function is evaluated and returns a result. Yeah, so no surprises there. And what happens is, this is just a function. Instead of having a header line, it refers to its right argument as omega, and I don't have a left argument in this case. Yeah. But another thing I could do with this function, let me just go up and modify this line, take this out. Another thing I can do in Dyalog with a function is to assign a name to it. So I could say, if I could type, okay, and in Dyalog, I can name any objects with assignment. So what this is saying is that mean specifies is the name of this function. And now, of course, I can use mean it's just a defined function. We're nearly there, we've nearly done Dfns.
But if you edit mean, do you see the very curly braces? Okay.
So that's a good, right, so if I edit, that's a great, so here's what I see.
Mm-hmm.
Yeah. And in fact, what I can do here, once I've got it into the editor, I can put a little air inside it, so I can just do that. Yeah. And now I can trace it if I want to. So in Dyalog, if I hold Control down and if I just hit Enter, it evaluates it. If I hold Control down, then I come up in the tracer. And this is the way I have my V12.1 tracer set up. I'm a minimalist. I like white, black on white. I'm not big on colours, although I could be persuaded. And in the tracer, the 12.1 tracer, I just get a little box around the current line. It's a little confusing in this case because there is only one line, but that's the line I'm about to edit. And then, of course, now I can tab back to the session, and I can say what's in omega, what's the shape of omega, what's the plus slash of omega, what's the paren SI, NL. And it's just mean. Can you see the bottom of the screen? Yeah. Okay. So please, if I'm introducing bits of Dyalog that you're not familiar with, I'm not. Just say, and then we can just knock that out. So there are no local names in this. There's just omega isn't a name. That's a good point. It never occurred to me before. It's not. It doesn't occur in this list. Alpha and omega are not named. Yeah,
that's great.
That's a good idea. Okay.
Omega is not a name.
They're a meta symbol.
I've found from experience that making omega a name is a big mistake.
Okay.
He was in the short omega, wasn't he?
Yes, it was. Yeah. It's a big mistake.
There's what I wanted to do, but I don't have a good internet connection. But on this memory stick, I put the reference. I feel very outclassed here. This is not just my normal false modesty, but Phil knows more about Dfns than I will ever know. Roger knows more about all of this stuff, including Dfns. You've been using Dfns for a couple of months, and already you're frightening me with the stuff that I see. And what I wanted to do was I thought this is going to be a really weird session. And I don't know if you're familiar with, I put the link on the thing. There's a Monty Python sketch called The Italian Class. Have you seen that? And it's a guy standing up teaching Italian at night school, and it turns out all of the people in the class are Italian native speakers. It's on YouTube, but the link's in there. So I was going to show you that to show you how I feel. Right. So that's just a simple function. So they're quite flexible. So anything in curly braces is a function so far. We've come on to operators in a moment. Omega refers to the right argument, and it can be used in any context that a function can be used. So, for example, named or unnamed. So one of the things I could do with this, for example, this is just a function. So I could apply this under the each operator to an array of 2 items. Yeah, and that again should not be a surprise. It can be used in any context that a function can be. It's just a function. Just a function. Okay, so we're halfway down the first column of the reference manual. The next thing, let me show you this. So what I'm going to do here is to give 25 So this is a function that gives me the nth root of its argument. So this is giving me the square root of 25, or the square root of... I wonder if I dare do a cube root of... Oh no. Well, trust me, that's correct. That's the cube root of 81. I could have done the cube root of 27, I guess. 64. Okay, the cube root of 64. So again, the next thing, again, we're nearly there. If there is an alpha, it refers to the left argument. So alpha's a left argument, omega's a right argument. And this stuff is not new. People have been using this notation in many APIs. I'm sure Sharpat used alphas and omegas in their direct definition. The various invocations of that. People have been using this for years. It's not a new thing. It's just an accumulation of stolen ideas that have come together.
Except that with Sharp's direct definition, you had to define it first.
You had to name it.
It was a static piece of code,
right,
that named the function. Then you could use it.
Okay.
You couldn't put
you couldn't use it. Okay, you couldn't put it in parentheses.
Yeah.
Yeah. Okay.
Definition and use it directly.
Okay. Okay. And that's a good point, because this is the functional programming paradigm. Part of functional programming is that functions are first-class citizens. They're not this. You don't have the arrays at one level and then a function of these sort of difficult-to-use objects. Functions in pure functional programming languages, functions can be passed as arguments, and they have all the same rights as arrays. This is not quite that, but it gets fairly close. Okay. So again, second thing in the reference manual: alpha and omega, left and right arguments. Let me just see what I've missed out. Okay, now I'm going to swap the order around slightly here. Now what I'm going to do is to look at my mean function. This is the next level. So I can write a lot of programming. I can write using just these alphas, omegas, just writing expressions in curly braces. Let me show you another. Here's a nice little thing. Where's the largest element? Let me think. Omega iota max reduction of omega is a nice Dfn, and that. Anybody guess what that might do? It's not going. This is just
locate the biggest.
Yeah, where in this vector is the biggest item? You know, is it at the third along? So that's an expression that might be used, and I could just use that in a line of code if I just wanted to do that, or if I was going to use it more than once, I might name it, and then I can use it just as a name thing rather than repeating it. And one of the things I'd like to impress upon you is that naming of things is independent of their existence in Dfns, and I think that's as it should be. We're used to that in an array. If I want the number 52 a lot, because it's the number of weeks in a year, I can either use that number 52 in my code, or I can name it. Particularly if I have to calculate it, I might want to calculate it and then name that so that I can refer to it again, or I might want to calculate it every time. So I'm not forced into naming things just in order to produce them. And what you'll notice is what I'll try to do is to talk about naming things rather than saying assigning objects. Because one of the things, this is back to the philosophy again, when I say, let's play a trick on everybody. If I say this, this is a good sort of litmus test for the way your thinking is working and my thinking is working. A lot of APLers, including me, see this as an operation that's going this way. What they say is assign 2 + 3 to I. They see this as brewing something up and then sticking it in a pigeonhole called I. And I think the functional programming paradigm is an inversion of that. And what they say is I names the result of this expression. They think about it as going in this direction. And they think about it, and some people, I think Ken Iverson would think about these sort of things quite hard. And at one point when I heard him talk, he referred to this symbol, he used the word specifies. He would say, I specifies 2 + 3. He may have used other words at different points in his thinking, but I'd certainly heard him say that. And I try to say I names, or if I'm being really pure, I can say I is 5. Yeah, I can say it. So, yes.
But when you say I specifies 2 + 3, in my mind it means that 2 + 3 sits out there, and every time you reference I, you have to recalculate the 2 + the 3.
Right, okay, that's
not what happens.
That's a huge, rich, that's wonderful. And that, if you'd have had that idea 30 years ago, there was a doctoral thesis in that statement. It's been done to death now.
Put braces around the 2 + 3 and you've done it.
So if I
put braces around the 2 + 3.
Yeah, that's true. Yeah, that's right. If I put braces
and
made that a function, it would have to recalculate it every time. Yeah. One of the okay, there's 2 jokes. Well, okay, you're not going to want your money back if we just tell jokes. There's a story about Ken Iverson looking over somebody's Fortran session in which equals. I'm not going to hit return on that because it'll. I wonder if I can make it scroll up or down. Can you read that? That's Fortran. In Fortran, this symbol means approximately the same as this in APL. And the story is Ken was walking by somebody typing Fortran, and they just typed that expression, I = I + 1, and he said, No, it doesn't. You walked up again. Because clearly I doesn't equal I plus 1. And his point, I think, there was to say this is not a good choice of symbol for specification. This is a better one. And we can use this symbol for equality. That was his point.
It's an equation with a solution, infinity.
It is an equation with a solution, and that's another doctoral thesis.
And that infinity, a solution.
Well, no. It may be.
That's
It's not. It's not. It may or may not be infinity. I'll come to. That's another doctoral thesis. One of the great. Well, it's the same thing. One of the great advances in functional programming came from. Let me write this again. Does anybody have a degree in geography? Okay, then it's okay. It's safe to tell this story. Well, a computer scientist was giving a computer science course to a bunch of geographers, and he was teaching a basic or Fortran or something, and they could not understand what this meant. He could not get this concept over to them, and it was bothered him. And he went away, and after a while, he realised that he didn't understand what it meant either. And he went, clearly I does not equal I plus 1. It's not a meaningful thing to say. And from those sort of ideas, the whole edifice of functional programming arose. And I'll show you, there's a little language which you probably don't know. There's a little toy language called min on your Dyalog CV, min.dws, which is a little toy functional programming language. And you can type this into min, and it's quite happy with it. It says, yes, I equals I plus 1. But if you try to say, now what's the value of I, it works its way through all of the natural numbers, trying to find one that satisfies that equation. And it takes longer than I've cared to wait for. And the functional programmers, in this sort of a statement, instead they don't say this. You've got to map this onto. To talk about this, you've got to give it a name, and they just they don't call it infinity. They say this is a special value which represents non-termination, and anybody who's been paid to write programs knows all about non-termination. You can write things that get into an endless loop, and the functional programmers, they just have a symbol to represent this, which they call bottom. And it is, they use this symbol to represent an expression that does not terminate. And they only have one, you only need one flavour of non-termination, and that's it. So they say I equals I plus 1 is an expression which evaluates to this. And you can do arithmetic using this value. You can do algebra, you know, if bottom plus bottom is bottom, and anything plus bottom is bottom. So that's, again, that's the way they deal with it.
To go back to my first comment, though, APL is not restricted to finite system or computers. It's mathematical notation.
No, absolutely not. No.
The primary traditional ancient idea beyond the natural numbers was called infinity in that solution.
No, it's only a solution if you redefine your number system, put infinity in as one of your axioms, and you can't, you know.
Yeah. You have to define.
You can't say 1 divided by 0 is
define.
infinity
Yeah.
unless you have.
But that's an older
carefully specified
definition than computing machines.
Yeah, it's like in arithmetic. If you say 12 divided by 0, you can either say that is undefined, that division is defined on all right arguments with this exclusion of the single item 0, or you can say it's defined as infinity. I think I've seen both things used.
But again, there's an older approach to this in mathematics before there were computing machines.
Yeah.
That has its own rich structure.
Okay. To this.
And APL can be used in that just
Yeah,
as well. So
sure.
APL is not limited to these things that are
No,
machine
APL is a language outside.
That's why I wanted to make that
machine.
point. If you jump outside the computing machine usage, the general mathematical notation, it's not meaningless right away.
Okay. So that was a bit of a tributary we went down, and I must now run a little bit to catch up. But the point I was going to make is a joke I'm fond of making is you've probably read this, you've all heard this joke before, but I'm an old guy, I tell the same joke over and over and over. You probably think this is a left arrow. It's actually a right pointing finger. So it says I points to indicates. If I knew Latin, I could tell you why indicate means the finger. Is it the digit? It comes from the same root. I indicates this expression. And there's nothing to say, just to wind this up, that this needs to be evaluated anytime soon. You might not want to do that. There's nothing in the language to say that. You might procrastinate and do it later on. And there are examples of lazy APLs with lazy evaluation that don't want to do it now, I'll do it later, maybe you won't want the answer. Yeah. So I try to say is or indicates. And I try to avoid saying I indicates I plus 1. And writing Dfns, it is possible to write very large programs without ever changing a definition. And we'll see how to do that. And in that case, you can write very large programs without variables, nothing varies. So that's what's... Okay, now we must carry on with some real stuff. So the next thing to say is, oh yes, let's look at our mean program. Which we wrote earlier. Now what I can do, this is okay for a small expression, but if it's a larger expression, I might want to chop it up a bit and name some of the subcomponents of the expression. Otherwise we get into this APL one-liner stuff where we got this, I bet you don't know what this means. So in general, I like to chop up expressions. And again, this is functional programming paradigm. The only reason to do this is to make it more accessible to me. What I like to do, and I would encourage you to do, is name chunks of my work so that they fit nicely into my quite small mind. So this might be too much of an APL expression for me. It might be too complex. So what I'm going to do now is chop it up a bit. I'm going to say sum is +/omega, and so I can replace this with sum, and I'm going to say num, just because I'm slightly autistic and like things to line up, is rho of omega. Should we test it before we ship it? Yeah. Let's go up a bit. What do we have? One more try. Right, so let's do a mean here. So let's run out. Yep, it works. Ship it. Okay. So the next generalisation is, well, what we saw before is a Dfn is just an expression involving alphas and omegas. And the new generalised definition is it me having an epileptic fit?
I think we all go in a minute. Okay.
Shall we call the cops or something? Shall we just do that just in case? It'll stop now, won't it? When you call the doctor, it stops.
I think you step on something.
Yeah, maybe. Let's go with it for a moment.
I think it was this one up like here, flash.
Oh, okay. Okay, well let's bear with it for a minute, but if anybody feels we should. So the extended definition of a Dfn is an expression. This is quite an important thing. I wonder if I'm clever enough to highlight that. A Dfn is an expression possibly preceded by local definitions used in that expression. Yeah? That's it. So I can chop this stuff any way I like. And this is just a simplification. It doesn't have any impact on the outcome. It's just a way of simplifying things. Yeah? And in a more complex interpreter or a more modern interpreter than Dyalog, that it would probably all squish down to the same thing. In Dyalog, these things are kept separately in the interpreter and evaluated one after the other, but it would be quite possible for an optimizer to come around and say, oh yeah, that's it would just reduce it to the original thing. It could squish it all down. But that's there. So I'm going to show you a little bit. Any questions before we? Yeah.
Two quick ones. If you have a fourth line, which is just num,
Yeah.
so num is going to display, and the
Yeah.
final line is what gets returned.
Yeah. Okay. Now that's a good point. Yeah, and you got me there. You got me. It's fair cop. This formally is not a Dfn now. It's not an expression preceded by local definitions. What we have here is two expressions, and that's an error. And what actually happens in the evaluation is, as soon as it comes to an expression, it's out of there, so it never gets to the fourth line, and that's a common error that people run into. Yeah. It doesn't, and it's as simple that, so it's just an expression preceded by local definitions. It's a very simple thing.
When you stated that definition first, was the Dfn is an expression possibly preceded by, is that what you said?
Yeah, but possibly preceded by. So our original version of mean, there were no local definitions in it. But no, better way of expressing it, more mathematically, preceded by 0 or more local definitions.
Could you run it and let's see could you run it as it is?
Yeah. And this is bad. Don't do this. Bad. In fact, I can put all sorts of syntax errors and stuff here. If I run that again, I get the same result.
So there's no bomb.
There's no bomb, and perhaps there should be. In fact, what I'll do is trace this, and this is informative. If I do paren SINL, show me the local names. What we can see here is there is an each on the stack which calls mean in a root space, stopped on line 1, suspended. If I do that, I have one local name, and it's important. This is so. The trouble is that I'm so used to this, I forget to say this. These definitions are local. It's actually quite difficult to have a Dfn make a global effect outside itself. You can do it, but it's difficult. There are tricks. Pips don't, and we'll come on to that afterwards, after the coffee. I'm going to run out of time. Okay. So what's happened here is this assignment here. Hi,
am I late?
No, you'll catch up. This is a slow crowd. You'll catch up real quick. So these definitions are local to the Dfn, and they disappear. So this is not making a sum globally in my namespace. If I go to, and they happen dynamically. At the moment, I have only sum. If I execute the next line and do paren SINL, I have both of these, and of course I could change that, I can edit it, I can do anything. It's just a local definition. Yeah. And then when I execute the next line, ready? Oh, sorry, I was running under an each, so I'm going in again. Let me do. That's going to be less confusing if I just take that each off and do it. Right, so let me just do that again. So here's my SINL. Yeah, now if I execute the next line, bang, it got an expression, got a result, I'm out of here. Yeah, so in general, a Dfn is an expression of alpha and omega preceded by 0 or more local definitions. And of course we can write this, I've chosen my words very carefully. I didn't say preceded by 0 or more local variables or local definitions, because one of the things I could do, let's change this sum to be a function. If I name plus slash, then that's a function. So in here, to compensate, I would have to say sum of omega. And I think, can I take this bad line out now? I think that's going to do the same thing. Yeah? But this time, I've defined a function and an array. I've named a function and I've named an array. Note the choice of language. I've named a function and I've named an array. Local definitions. You don't like that? What would you prefer to say?
You can name a function, but you can't name an array. You've done a calculation, you've dropped it in a pigeonhole. I'm sorry.
Yeah, I know. Okay. That's a huge wrench for me. The FP guys say use this sort of language, and naming is just a little. Well, I think one way to get this. I mean, this is really good. If you can just get an inkling of this and practice in front of the mirror at home, see how it feels. One of the things with naming is it's a little. You can imagine a great long expression. Let me write some great long expression of APL. So here's APL. Scribble, 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 scribble. Friend. So this is a line of APL, and that may or may not work. And one of the things I can do is say, I understand what that little bit is doing. Hey, I understand just that bit. What that's doing is calculating a standard deviation. So I'll call that stdev, and I'll name that bit. So I can recast this line, scribble, 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 stdev, scribble, scribble, scribble. Oh, and I understand what that little bit there is doing. I'll name that. So you can go in, surgically remove a function or an array or a function expression and replace them with names just for your understanding. The interpreter doesn't care, because when it comes along stdev, it's he means this, and he just substitutes it. So it's a good practice. I was brought up on procedural programming, which is this pigeonhole and shoving stuff in pigeonholes. And when the going gets tough, I'm straight back there. I can't. I can talk the talk, but when the going's tough, I don't continue to walk the walk. But it's a good exercise, unless people, you're sold by this. I think there's a body of FP philosophy that goes along with it. So this one again, let's just test this out. So let me do. So I take those parens off because I'm wondering. I wonder why this. So first of all, test it. Yeah. Okay. So in this case, I'll run this. What's in sum? Oh, sum is plus slash. Num is 4, so if I apply plus slash, so sum of omega is 10, and 10 divided by 4 is 2 and a bit.
Can you just type mean, see what it does? Enter mean.
Oh yeah. I think we're all going to be disappointed.
Oh.
Yeah.
Why can't it show plus, like what it did for sum?
Yeah, wouldn't that be good? There's for historical reasons, the FRE does show that. But there was we produced an experimental version of the interpreter 2 or 3 years ago called the Function Results Edition, and I dinked around with a lot of that stuff. And what it did, effectively, if I typed, then this is my selling pitch. This is reductio ad absurdum argument. If I type the name of an array, APL would show me the array. If I type the name of the function, APL would show me the body of the function, and I like that. And the counter argument has always been, yeah, but what if it's a 1,000-line function? Well, what if it's a 1,000-line array?
Yeah.
Well, I type row array before I typed its name. Yeah, well, you could type row quad CL function. Yeah, but I don't want to type quad CL. So it's available. If you want to download the FRE edition, which is a version, it's a souped-up version 9. It's got all sorts of nice. I would say that it's got little tweaks, including that, and I would like to do it.
If you actually just type the one-line edition of mean with no names in it,
Yeah.
without naming it, with the braces. No, if you just...
Oh, so if I just type it, yeah.
Just type.
Well, can I do
That
something
reflects back
easier?
to
So alpha plus omega, would that be okay?
Yep.
Yeah.
So if it's not named,
There's no excuse. I don't know what that. I don't know. That's just because it's gone off somewhere in the interpreter that thinks it knows what it's doing, but it doesn't. It shouldn't do that. It should just. I think it should just put those
that.
1, 2, 3, 4, 5 characters here. That would be nice. And the FRE. I wonder if I've got that. I wonder if we got it. What about the FRE? FRE. Damn. This is a wonderful FRE. Hey,
Yeah,
that's
yeah.
what it should do, isn't it? Oops. Well, yeah, whatever. Hey, that's what it should do. Yeah. But
How did that happen? What did you do
This-
differently?
this is a special doctored. It's like
it's the
the
doctored-
Lotus.
oh, okay.
Suit, you know those little Lotus sports cars. It's a cut down interpreter with all sorts of. Got a souped up engine, twin carburetors.
But some functions can be nil-adic when returning.
Ah, you say that, but you'd be wrong. Okay. That's a good point. You can't have a nil-adic defin. You cannot have a nil-adic defin. And partly that's because of the syntax. It's awkward. You get into horribleness when you try and... Well, for instance, if I were to name that, you can't tell whether it wants you to evaluate the nil-adic function and name the result, or name the nil-adic function. And
Well, the same with running the function and seeing the code. You can't type mean and expect to see the code if mean is an actual function
That's easy.
that runs.
Just outlaw nil-adic functions.
yeah, that's true. Sorry, that's true.
Okay.
Sorry, that's true. Yeah. And we don't have time. I rant about. I go off on a religious jihad about. A nil-adic function is an oxymoron. There's no such thing. A function is a mapping from.
well then see a nil-adic thingy in APL should not be 3.
Yeah. But you know, there's a lot of history. You got to, you know, we can't be completely revolutionary. Okay, so where did I get to? Why doesn't it do that? So we're running a little bit. I need to speed up a little bit. But that's okay. We're still there. Right. So we've done that. We've said that local names are dynamically defined, so we name local values, we name functions, and we name arrays. We've done this chopping, so in any time you've got this freedom, you can chop up expressions just for ease of understanding. That's the only reason to name things, is ease of understanding. And it's the best reason for naming things, and it's a good, do it. Chop things up, name them, so that you've got a chance of understanding tomorrow what your code you wrote today is doing.
When it show +/ for some,
Yeah.
it knew to do that because you're suspended.
Yeah. Well,
My question is, suppose you define sum to be, you name sum for a thread fund inside a dfun, and then you type sum. What would it show?
inside a dfun, I'm using the name tradfun.
You name a thread fund in a dfun,
Yeah.
and then you just type the name while suspended in a dfun.
Oh no, it's nothing to do with being in a dfun. If that was true anywhere, if I type the name of a function in Dyalog, if it's a nil-adic tradfun, it will execute it and display the result.
No, I'm not talking about nil-adic
Okay.
functions.
Yeah.
I'm talking about your being able to display plus slash for
Do you
SUM.
want, do you want functions always display as the derivation?
Yeah, so if I just type plus
Well,
slash, it says
anyway.
plus slash.
But if some were, left brace plus slash omega right brace, would it show that while you're suspended? Oh, so it's not the suspension.
No, it's nothing to do with the
Okay.
suspension. The only thing the suspension is doing is local. We have those local
see.
names, and I could be defining those globally.
I see. Okay.
Yeah.
But if you define sum to be 55 as a variable
Yeah.
outside your define,
Yeah, that's a good-
inside you can still use
that's
it.
good. 55. Right, so let's run this function again. So if I run this, and that's because it's local at this level in the suspension. Yeah, it's just
That's
shadowing,
normal.
that's all, yeah, that's all. So there's nothing definy about that, it's just the definitions. Yeah. Right, now where have we got to? Right, so we've done that, right. So the final working part, a Dfn is about the same level of technology as a bicycle. There are about 3 moving parts. Here's the next one. No, before I do that, I'm going to tell you one more thing. Okay, this is a bit more philosophy. This is a bit more philosophy. This is one of these things like the pigeonholers of the naming. In a regular language, Nobody's here watching me. I can just type in. Okay. And this might be an expression with lots of stuff in, and this might be another expression with lots of stuff in. We see. Well, I don't know about you, but I see this as sort of 2 levels of stuff going on here. There's a nice world of expressions, and then there's this outer level, which is almost a separate language. It's a separate, has its own rules. It's you have to read in the book. It says evaluate this expression. If it returns a 1, do this stuff, and then jump around and don't do that stuff. But if it returns a 0, do this stuff and don't do that stuff. It's a separate. It's like you go to a separate class to learn. You learn your expressions in one class, and you go to a different class to learn these. Now, one of the things the functional programmers did is to say, wouldn't it be nice if this all was the same homogeneous unit? And the C. Does anybody write C? Anybody ever writing a bit of C? Yeah, a little bit. C has this in C. Modulo my ability to remember. You can say if stuff, do this, else do this other stuff. I think that's all you need. You need to pepper it with semicolons. Okay. But C also has this other thing. I don't know if you've seen this. You can say if this stuff, then this, else this. Have you seen that in C? And these 2 things here are like an if-else in the C language. Yeah. And what they mean is, the rules are that it evaluates this. If it comes to anything other than 0, that. Otherwise, if it comes to 0, do this. And the nice thing about this is you can put this whole thing in a bigger expression. It's just an expression. So it's really a triadic function in C. Whereas this you can't put, and this you can't put in any. What I can't do in APL is to say A names if that 5 else 6, because it ain't that kind of gal. It won't let you do that.
There's no intrinsic reason why you can't.
No, that's true. That's true. There's no intrinsic reason why you can't. No. Okay, that's true. No, okay, that's a good point. That's a very good point.
Sorry?
Does Johnny know that? Because you've got unit control. They're in line with that function.
I mean, what you have to, in general, you have to decide what the result of a while loop is, or the result of a for loop. I think Algol did that, and it was the while loop was the last thing you were thinking about before it exited was the result.
There's a special syntax in Algol.
Okay.
If then else and while.
Yeah. But I think a lot of those could also be used as expressions.
Yeah.
Yeah. And again in APL, sometimes it's nice to write this, but sometimes it's really cool to say the Boolean pick of this one or that one. So if it evaluates to a 0, give me this one. And if it evaluates to a 1, give me this one.
So you've got to evaluate both before.
Yeah. Okay. And that's the problem. So Dfns has one of these, but with a lazy evaluation, which allows you only evaluate one at a time, and it's like the C one. And then the way you do this in Dfns is do my condition colon true stuff else false stuff. So let me do. So this is like the C equivalent. So sorry, most functional languages have this sort of construct, and they have they have an if like this. The way we do it in Dfns is with this thing here called a guard, and this is the last moving part of the Dfn. So what I can say here is, let me write one.
Have you got an F key set up to do that?
Sorry?
Have you got an F key set up to do that?
Yeah.
Okay.
Yeah. Come to my session whiz bangs talk. I've got a fun. I did. Let me show you this. I'll show you in a moment. That'd be. Yeah. What would foo? If I do ed foo, what I can do is if I type F9, I think it's Control F9. It does that for. Oh, actually, it should do that as well. Control F9 just puts those, because I do that such a lot. It's nice to have a function capable. On Tuesday, I've got. If you know, it'd be really good if you could come. I'm doing a session on session whiz bangs, all sorts of little tricks to ease typing in the session. That's what it is. Yeah. So what this guy is doing, this is the only other moving part of the Dfn, is it evaluates the thing to the left of the colon, and if it evaluates to a 1, then the result is the evaluation of the thing immediately to the right of the colon. Otherwise, it's the thing following the diamond. And that's exactly the same as this stuff and this stuff and this stuff. So shall we just test it? Yeah. And what we'll do here is to do parent 3. Let me edit this. And what I can do is split this over a couple of lines. So if I put this on a separate line, I don't need the diamond. Yeah? So you know diamond's just the same as a new line in APL. I think that's true. More or less. Yeah? Yeah.
So the reason you can't put another line is because then you already passed your evaluation.
The reason, sorry, I can't put it.
Move your cursor down
Yeah.
and put try this.
Yeah.
And you'd never get there because
I'd
of what you
never
said
get there
before.
because that's the again, once this guard is fired, then I'm back to the original. This is the final generalisation. Notice it's just one more generalisation. You know, Dfn is an expression preceded by a number of zero or more local definitions. There's this one extra thing called the guard, and that is as I've described. So effectively, what this is saying. Let me just do this. Well, let's evaluate this. So if I do parity 3, it's going to calculate 2 residue omega. What do I get left over when I divide omega by 2? And that's a 1. So this guard is evaluated to a Boolean 1. So the result is quote odd quote, and it will never get to the next next line. But if I did parity 66, then 2 residue omega is 0. So sorry, I did that. Let me go in again. I skipped too far. Okay, so 2 residue omega is 0, so it won't execute that line, it will go on to the next line. And the result is even in this case.
Are there any restrictions on condition? Does it have to be a scalar, for example?
Yeah, there's one of those. Yeah, that's one of those things that we tied it right down. It has to be a single. I think it probably has to be a scalar or a one-item vector. APL's a little bit lax about one-item vectors.
Whereas the right operator power has to be scalar.
Oh, I didn't know that. Okay, well that's interesting. Maybe that's.
So it's similar to the select and then case and case and case
Yeah,
and select.
exactly right. Yeah. So one of the things you could do here is let's write another one. So if I say omega is less than 0 neg, omega is greater than 0 pos, otherwise, and that's just like a case statement. So if I now run that with sign of 0, it's going to say, it's just like a case statement, yeah. It evaluates this expression. Oh, I put a mouse in the way. It evaluates this expression, this arbitrarily complex expression, which of course can have other Dfns in it or anything you like. It can call other functions. But whatever the thing to the left of the colon, it's got to return a 1 or a 0. And if that returns, in this case, we gave it a omega is 0, so that's false, so it drops onto the next one. Is omega greater than 0? That's false, so it drops onto the next one, and now it will just return. So I can have any number of guards.
Yeah. Can you put the 3 lines on one line using diamond?
Yeah. Diamond is just the same as a new line.
So the diamond guard's parts can each have a guard.
Yeah. And if you're looking at this model, you can there's an association. Actually, C does exactly the same thing. This, I can't remember. This stuff binds. It binds the right way round. I can't remember the binding, but in C you can write this query that, else this query that, else this query that, else this query that. You don't need parens, and then it will just drop down like. There's C. If you can write C to look like this stuff. Yeah.
Where you have neg,
Yeah.
can neg itself have guard? Have
No,
condition?
no. If you put braces around it, there's an argument for saying that we should extend it to do that. No, it has to be an expression. But that expression could be braces with anything else inside it.
Braces.
It could be braces applied to a... so typically, this is a nonsense function.
Braces but not parens.
Another default.
I could have another detail. So for instance, I could say if... you see the syntax coloring's complaining because I got mismatched. So typically, if I wanted to do some tricky stuff here, I could then do other stuff within. Okay. So then I could subdivide. I could say if omega is greater than 100, do stuff. Otherwise, if omega is greater than 50, do other stuff like that. Otherwise, yeah. You don't like it.
The problem is you have to mention the omega
Yeah.
bottom.
Yeah.
And it gets more complicated when you have operators, because then you have to mention the alpha.
Yeah.
Well,
Yeah.
I'm
We'll
getting
come on
ahead.
to that in a minute. Yeah.
you have to mention.
You
up
could-
to 4 arguments.
You'd have to define an association order, which you could do. It has occurred to me. I've been tempted to do that. It's the same. The same thing in C. If you got ifs and elses, you've got to decide how they bind. But we could do that.
Because you've been talking about the world of expressions.
Yeah.
But to do this, you're basically dropping out the word.
No, these are expressions. These are expressions.
No.
Yeah, they
It's
are.
not. If it's an expression, then you can use parens.
That's it.
And then the colon would be part of the world of
Colon is not a
expressions.
function. Colon is
No, colon is not a. It's not a function, and the reason it's not. It's not. I pretend it is to a less discerning audience than you are. It is because in APL we have strict evaluation, so it's not. In APL it evaluates everything, and this is a bit of syntax. But what is true is the thing to the left of the colon is a bool single returning expression of any complexity. So again, this is going to be horrible. But this stuff, instead of that, I could say what. Of course, I can do this. I can do any arbitrarily complex expression that yields a 0 or 1, and then it applies. If that's true, then it evaluates the expression to the right of the colon. Otherwise, it evaluates the thing to the other side of the diamond. Yeah.
If the right side of the colon is just too complicated, I can just write a traditional function.
You
Big kill.
You can if you want.
Yeah.
You can call anything. Yeah, you
Right.
can call anything. True. That's
Then,
true. Yeah.
Then I can have very complicated stuff.
Yeah. Sure.
I'm not restricted to just dynamic function.
No, you can dip in and out
Yeah.
of
Right.
D functions. Yeah. Incidentally, just one point. I've been trying. I mean, this is the work of lots of people over lots of years, and when we came up, we got all of this stuff ready to show at the conference. The only thing we hadn't got was a name for what we were showing. And we couldn't think of a name for this stuff in curly braces, and people thought bubble functions and then somebody said, well, dynamic's a good name, and it really isn't a good name, and I've been trying to get away from that. So I prefer to call them just D functions.
But the reference manual called it dynamic function.
I know, I keep crossing that out and changing it every time I
So
get
we
to...
should let Dialog know that they
Yeah.
should change the reference guide.
Yeah. I'm probably the only person that cares deeply about that. But sorry.
If you go to pause and 0, those
Yeah.
two lines,
Yeah.
and insert a line between them,
Yeah.
and that line between them does not evaluate, let's say, Roy gets 5. Is it going to hit the 0 line and still say 0?
Yeah, because this is, yeah, that's a good point. Okay, my simplification, my beautiful simplification is in tatters.
It's not just a single diamond, essentially.
No, it's the other rules apply.
Yeah.
Then what we have here, the result of the thing following this is back to the rules of it's an expression preceded by 0 or more local definitions. And I have to, okay, I haven't quite got this right, so what I'm going to do is I'm going to be a scoundrel and resort to procedural thinking rather than functional thinking and tell you how it works. And I shouldn't have to do that. And it's either a symptom that this stuff isn't quite right or it's a symptom of my grasp on it isn't quite right. But the way it works is the stuff just comes down from the top. If it comes across a definition, it just defines it and carries on. If it comes across a guard, it evaluates it and carries on. If it comes across an expression, you're out here. Yeah, I'm humiliated. I nearly got away with it.
I hesitate to slow you down.
No.
Can you say omega gets omega times 2 inside your defined
No, you can't. There's no reason. No, there isn't. Well, go to what Roger said. Omega is not a name. It's a special thing. It's almost like you can't say 3 gets 2. It's that sort of it's a lockdown.
And can you have line labels in Dfns?
No.
Then that would conflict with
in
your
fact,
guard.
no, they would conflict with the guard. That's right, and that's the really nice thing is we could use the colon, which is exactly the right token for a guard. It's exactly the right, from a use of grammar and, it's just, and it is available because we can't have that. And you have within Dfns, that's the only control structure you have is a guard. You don't have loops. You don't have. If then else is you don't have force, and it turns out you can do everything with that, as we'll see.
Or branch,
You don't have branches, no, you can't do that. And it frees up the right arrow, we can think of uses for that.
Oh, I hope you know.
Yeah, should we carry on? Are we good? Okay, so I'm going to kill this. What do we get to? Right, now, having said all the things having told you can't say omega gets, did I define something? No, I didn't. Do you remember this guy? We did this early on. We said omega divided by omega to the power, the reciprocal of alpha. And what that was, I could say, what's the square root of 64? What's the cube root of 64? And a lot of times in APL, I don't know if you're writing tradfns, it's my tradfn. Now tradfn, this is a traditional function. Z gets L trad R etc. That's a tradfn. And in my tradfn code, the first line is often execute the 0 equals quad NC of L slash L gets some value. Are you familiar with that? Yeah, because in fact in Dyalog, if you're going to play that game, you have to put braces around this guy, otherwise you get to say we allow that to be there or not. But that is such a common construction. That's a way of supplying a default argument to a dyadic tradfn, so that if the guy calls it monadically, you can give a default argument. Yeah, so people seen that? It's a trick. Okay, and it's used so frequently that in Dfns we have a little slick bit of syntax to do exactly that. So what I'd like to do with my, let me just, what I'd like to do is to make this so that it defaults to the square root. So I'd like to give alpha a default value of, are we flipping? Let me get the guys. Let me get the guys because it might blow.
It's really got the loose connection.
With the power to the projector.
Give my click the keyboard.
They're not falling out.
Yeah.
Mine died the other day.
But I think he wasn't seeing it when he was looking at the screen, right?
No, he accidentally stepped on that wire again. See? It's lost now.
Do you want me to pay up?
Lost now.
Well, sorry? Was it when I trod on it?
He just jiggled the
That's easy,
wire.
I won't tread on it. Okay.
But were you seeing it on your screen, or was it just the projector? Your screen wasn't going with it.
No, I didn't notice
Yeah,
it.
then so it's the
just
power of the projector.
Oh, right.
Yeah, sometimes it does it when you're not even near the line.
Yeah.
Well, we'll get Jason to have a look and see if he can come and tread on it. And we've got, what have we got? Another 3/4 of an hour. We're good. Okay, so what I'd like to be able to do is to type root 66 and get the square root by default. And so there's a bit of special syntax in Dfns to assign a default value to a missing argument, and we say here alpha gets 2 diamond. And I can put this on a couple of lines. And it's important to understand what this means. It's quite, once you get used to it, it's okay, but it's very easy to confuse it. What these two characters taken together are a piece of special syntax, and what they mean, these two characters are, if alpha is not supplied to this function, then run the expression to the right of the line, evaluate the expression to the right of the alpha assign, and make that the value of alpha. If alpha is supplied, then don't run the expression to the right of the line. It looks a little bit strange, but once you get used to it,
Can I do that to omega?
no, only to alpha. And you can't, yeah, it's not the way to call it. No, that's right, you can't call it without omega, so it never arises. You can't do that. But omega assign is a piece of syntax that's reserved. You could do that.
In one line, you put something between the two.
So again, it's
In one line function, if you will.
yeah, well, no, you'd have to use a diamond. You can't do it in
Yeah.
just one line. You have to use a diamond. It's special syntax. But in particular, this can be any arbitrarily complex, whatever. And the thing here is, if alpha is supplied, then this won't be evaluated. If alpha is supplied, it won't be evaluated. If alpha is not supplied, it will be evaluated. So in this case, then I can say, what's the root of 66? Or the cube root of 66. And if we go back to okay, well, this is progress we've made. Actually, I should be able to point, if I put the mouse on, oh, too late. What we've seen here is every year I get called by this. When I practice this carefully on my laptop, set the font up to a nice size, and when you plug it into the projector, it squishes your screen down, so we've missed a little bit off the end here. but what you can see here is this piece of syntax. It's a special slot in here. So we've seen the guard. We haven't seen error guards yet. We've seen this, and we haven't seen SHA results yet. But we've seen this column. So we're halfway through. Dfns. I would urge you to load or look on the web at the Dfns workspace and look at some of the code that people have sent in. And also, if you have some examples, we'd really like to see them. It's fun to see little tricks and examples, and we'll put them in the workspace. It's really good. What you have to, the rules are that you have to provide for three things: a function, and shows you how to do this in the workspace. A function, some notes that describe the function, and then some test cases that we can test. Let's show this working. Okay, so here's an example. Copy Dfns. This is the first Dfn that we ever showed anyone. So here's a fully paid up Dfn. This finds the real roots. It's been out of date now because we're going into complex numbers. The real roots of a quadratic equation. Do you remember that from high school? So it was this bit at this guy. I'll tell you what. Let me spring the mouse out of my bag and then slightly less. That's that, right, okay. So, you remember this is b squared minus 4ac. Do you remember square root, what is it? Plus or minus the square root of b squared minus 10, whatever. So this is a really quite a... that shows most of the moving parts of the Dfns we've seen. So given three values, which are the coefficients of ax squared plus bx plus c, what are the real roots of that equation? So first of all, we name. We don't poke omega into three separate pigeonholes. We name the three parts of the three-item vector omega, a, b, and c. I'm told this is called the discriminant in math circles of the quadratic. Looking at John for approval here. So this is just an APL expression which we're naming the result of. And then we say if the discriminant is less than 0, there are no real roots. If it's equal to 0, there is one root, and if it's greater than 0, there are two real roots. Yeah, so that's an example. And this is slightly strange. I've done this just for completion. These two guards together preclude the last one. That last guard is not necessary, because if it's not less than 0 and it's not equal to 0, then it's going to be greater than 0. But just for readability, it sort of works nicely that way. And that's an archetypal, prototypical, model Dfn. And we can see we've got there's one piece missing, which I'll show you next. Yep, so far so good. Yeah, these are all in the Dfns workspace. And usually you can Google this stuff because it's all on the web. If you Google Dyalog space quadratic or something, in the first dozen hits or so, it'll take you to one of the pages where you can look at this stuff. And typically you'll come to the notes, and then at the top thing in the notes there's a link to the code, and then at the bottom of the code there's a link to the test cases. Yeah? So far so good. I think the final thing in this section is, it says here, divide and conquer, recursion, recurrence relationship, fear not. there's this great technique in maths where if you've got a problem and you can split it into two separate, slightly simpler problems, you're done. It's great. And I used to, when my kids were of an age to listen to me until they were about 4, I used to tell them this gag about President Kennedy. That one time now when would that have been? In 1956 or so, he decided to put men on the moon and bring them back safely. That was his mission statement. You know, how do you do that? That's a really big problem. It's really easy. You call 2 guys into your office. One's a rocket guy, and the other's a space capsule life support guy. And you say to the rocket guy, I want a rocket that'll go to the moon and come back again. And you say to there's the life support guy, we need a capsule that's going to sustain life. And the rocket guy calls 2 guys into his room and says, we need to build a rocket to go to the moon and back. We'll need this payload and this payload, and we need. And you just keep subdividing the problem until you get to something you can understand and deal with. Right at the end, there's 2 guys saying, like, we need a nut and bolt. You go and design the nut, and you go and design the bolt, and they actually do it, and then it percolates up. And I've got a feeling that Aristotle invented that way of. I've got a feeling, or he put a name to it. This divide and conquer thing. It's a really powerful technique. Okay, and I suppose we've come across this with subroutines when we're writing our programs. Sometimes if we're showing off, we try to write them top down by saying, I'm a clever guy, I can just write this and then we'll call this and this, and we go and write this and this. And actually it doesn't work, you wind up fiddling around with it. But divide and conquer is a really good thing to do. And it just occurred, this was one of these sleepless nights, in the middle of the night last night, it occurred to me a nice example of that. Here's a good one. This geezer called Euclid. Is that how you spell Euclid? Okay. And he lived from approximately minus. I'll get it in a moment. Euclid's GCD. Okay, well, if I give you 2 numbers, the trick is, can you tell me the biggest number that will divide evenly into both of them? So a good example might be 30 and 42. What's the biggest number that will divide into both of them? So number 3 will divide into both of them. Oh, it's number 2. They're both even, so 2 will divide into both of them. It's a big one. 3 will divide into both of them. Do you know how you tell if 3 divides into this?
Yeah.
Add up the digits.
You add up the digits, yeah. And if 3 divides into that, then you keep adding them up until you get a single-digit number. And if it's 3, 6, or 9, then 3 divides into it. Yeah. So and then so 2 divides into it, 3 divides into it. So 6 divides into those. Is there any big one? What does that not? Okay. And I believe this is the way that Euclid thought about this. Well, he's not here to dispute this, so I can say anything I like. Is you draw 2 lines. The Greeks were into geometry, so let's draw one like this and one like that. Now, if a number will divide evenly into that, what I can do is make a little number, and I can walk it along here, and it will hit the end, and I can walk the same number along here and hit the end. Now, one of the things is, if whatever number that is, if I walk it along here and hit the end, I can switch to here and walk along here with the same number, and it's got to hit the end of this one. Yeah. So one thing I can say is that the biggest. So I could go in little itsy bitsy steps, and both of these, like I can go along in 2s, or I can go along in 3s. So what's the biggest number I can do? And the biggest one, we'll still have this property. If I can walk along here, if it divides into this one, then when I get to here, it'll step there, and then I'll go a certain number along again, and the same here. So a way of making this problem simpler is, instead of dealing with this big number and this little number, I can just deal with this number and this number. It's the same property, so I can copy this down to here and do the same thing. I can walk a little itty-bitty number along here. Okay, and then if that's true, I can, what do? I chop, now I'm flummoxed now, I think I chop this amount off that one, do I? Yeah.
Let's do
Well,
it.
you can do it exactly the same. Chop it directly above.
Chop it here.
Yeah, and bring the right bit down.
Okay, bring the right one down, yeah. Bring this one down, do I? Or this one down?
The big one.
The right one.
Smaller
The
one.
right one, okay.
The right one.
Okay, and then I do the same thing again. So that's the way. So all I need to say is, to solve this problem, and this is one of these mind range things again. Instead of saying do this, then do this, then do this, then do this, what I can say is the solution to this problem is just the same as the solution to that simpler problem. That's it, done. I'm out of here. So if I can just describe this problem as a simpler problem, then that's done. And he said there's a very strange case here. What if I had the greatest common divisor of 5 and 5? The biggest number that would divide into both 5 and 5 is 5. So if we look at that, what we do is we chop this guy off at here, and we copy this down to a 0. So this is saying what's the greatest common divisor of 0 and 5, which seems a bit strange, but that's okay. 5 divides into 0 how many times? 0. So that's okay as well. So what we can say is, if one of these numbers is 0, then the answer is the other one. Otherwise, it's the GCD of the difference. And that was Euclid figured that out. But the interesting thing is we don't need to define do this, then do this, then do this. We don't need to write a umpteen-line program, do this, try it again, do this, try it again. What we can do is give a strict definition. So let's have an attempt at writing a GCD.
Just out of curiosity, did Euclid know about 0? Did he actually say
I
0?
don't know. And I need to know that because I've foolishly tried to talk to people about complex numbers.
It might, rather than being 0, you could define that as being if they are the same.
Yeah, he might have
If the
stopped
number-
one short. You're right. Yeah, he might have.
I'm just curious,
Yeah.
because that would have been a
Yeah.
fantastic invention.
Yeah, no, I think you're right, he didn't. So what we'll do is we won't use 0, we'll write it again as Euclid may have written it. Okay, so here's GCD. So what we're going to say, so in this case we're going to say if alpha equals omega, then omega, or alpha, it doesn't matter. Yeah. Otherwise, I'm going to get this wrong. The thing is the minimum. What do I do? I can't remember. My mind's gone blank. It's the minimum. I think I can just say omega.
You take the maximum minus the minimum.
I think I can just take either of them
I think,
and the difference. No, the biggest and the difference. The smallest and the difference.
The biggest minus the smallest.
Yeah, I think I can take
Or
it's
absolute
the
value.
absolute value.
That's right. I think I can take the difference, alpha. Let's take the minimum. This GCD of the absolute of the difference.
Well, the difference of the absolute. Yeah. Yeah.
Might this
Sorry,
work? I don't know if this will.
no, you're right.
We're
You're
pioneering
right, yeah,
this.
it's a difference.
Might this work? If this doesn't work, I'm going to quickly copy the correct solution in without thinking about it.
Right.
Hang on. Oh, actually, that is instructive. You can see the error message. It didn't like. There wasn't an alpha. Dialog's a little bit artistic about where it draws its caret. It should have drawn it directly under the alpha there. We are attempting to fix that. Let me see. Oh, look at that. That took a while. Okay, so that appeared to work.
Try 30 and 84.
I don't know what the answer for that was. That good?
Yep.
And 84 and 30.
It just doubled to 42, but there was no
Oh, yeah.
extra power of 2 and 30, so it didn't
So this is
change.
why I need an APR key. If we switch the arguments the other way around, that works. So what we have here. Now this is one of these mind wrench things. Let me try and get Joe. Oh, that's because I stood on it again, isn't it?
No, you stepped away. So.
Has it stopped?
Yeah.
Okay. I'll try not to stand on it. Now, there's two ways of thinking about this. One is we're thinking about, when we read this, we can think about it in the old-fashioned way, which is, oh yeah, it's going to do that, then it's going to do that, and it's going to call it again, and then it's going to do that, and it's going to do that, and it's going to do that. I'd urge you to practice thinking about this as just a definition of a recurrence relationship. The GCD is, if alpha equals omega, then it's omega. Otherwise, it's the minimum GCD, the difference. That's it. We don't need to know how it works. We're just specifying, and we trust. If we get good at this, we just trust. I mean, that was pretty. That was new code that we wrote between us. You know, we didn't. We just said that. Yeah, that should work. And hey, it did, which doesn't happen to me very often. Yeah. And this is the final part in the Dfns thing, that we have there's no looping, there's no while loops, there's no anything. The only thing we have is recursion. This is recursion. Yeah, so what we've done here is to take a problem, we've said if it's a trivial case we've got the answer, otherwise we've split it into sub-problems. It's a powerful technique. And it's so powerful that it's used so often, it's so frequent in Dfns, and because you don't have loops and things, that there's a little trick we can use here.
John,
Yeah.
let's just trace it first.
Oh yeah. Yeah. Okay, so let's do it with the original 42.
Oh, but it's
So the 84 is better.
no, it's term recursive anyway,
Yeah.
so it won't work. I will still show you.
Yeah, so yeah. So
Go round
what we
it,
can do, I'll tell you what. One of the things we can do. And this is really after coffee break stuff. This is a little trick. If I wanted to display alpha and omega as we were going through, if I put alpha omega here, then that's not going to work because it's just hey, we're done, we're out of here. But if I pretend I'm defining, if I'm saying something is alpha omega, and that something could be a quad, then it's just going to make that specification and carry on. So I can always put a quad in there. So now let me see. So now we can see here, that's not a surprise. Alpha is not equal to omega, so I'm going to go, so if I trace this line, I get 1354. See, now they've switched. Alpha equals omega, yes. We've done. Yeah? But that's sort of for unbelievers. So, I mean, there's great myths. The functional programming guys are great. I mean, they're my heroes. I think of these guys as living up in this temple in the mountains somewhere, dressed in saffron robes. And the real, I mean, I heard stories about this in the 80s. The real big advances in functional programming came, and the real guys didn't use computers. They just used pencil and paper. They would say, yes, this is the GCD algorithm. That's it. Take it. Because they were so confident in the techniques that they didn't need I have to, run it under the debugger, make sure got it right. These guys were very they were like aesthetic monks. They would, and funnily enough, a lot of them had APL backgrounds, because arguably APL is one of the early functional programming languages, because it has this purity of style. And so some of them, in fact, one of the names is, I meant to bring this in, but I forgot. Did I forget? I forgot. Oh no, I didn't. I can't let you have this, but this is what did it for me. This is the Computer Journal, the British Computer Society, April '89. This is what first hooked me on functional programming. I can pass it around. I can't let you have it. But it's a special issue on lazy functional programming, which is lazy is the purest of the pure. It sounds like a derogatory term, but it's one. And this just describes what you. I mean, if you want to pass it around, if you want to take a note of the name, you can. I'm sure you can get it from your local library, a copy of it from your local library. But that's what first got me interested in this sort of stuff. It's got some nice examples. So the point I was going to make is that there's little to go wrong there. So we could just write it theoretically. If we were very clever, we could just write that down and have a high degree of confidence that it was correct.
Well, if you say 0 GCD 5, you'll find out what happened.
Oh, will that not work?
No.
Oh no, it'll go forever. So it's not correct. There's a bug in it. That's right. That's a bug, and that will not terminate, will it? It'll subtract. Yeah. So you're right. Oh. Okay. Yeah, that'll go. Let's do it. Okay, that's not going to get anywhere, and that's an example of non-termination. That'll teach me to be confident.
But Euclid didn't have that problem, did it? Because
He didn't have zero.
zero anyway.
No.
He didn't have zeros in
geometry.
His geometry. Yeah. No, he needs a zero. There's a gag. There's a gag. What? I need to talk a bit about numbers tomorrow night. I'm talking about complex numbers. So let's start with numbers and work my way towards complex. And zero is a really interesting concept. It wasn't needed. You get by a long way without a zero. You get what do you call a shepherd with 0 sheep? Unemployed. He's not a.
It was only when you had
didn't do anything at all.
started to develop commerce with several businessmen all had to be able to each make money.
Then you
Break down the whole into every individual, zillions of them.
Yeah. You need that. So I didn't get. Maybe I'll just step near that. Did I or do I step?
You didn't do anything at all. It started flashing then. You were already here.
Okay, I'll get Jason to sort it out when we have some coffee. Okay, so I have a bug. You're right. I have a bug. That's not a. It would have worked for Euclid because he didn't have a zero. This is a non-zero proof. Okay, and I think here, if we were to say, would this work if we said 0 equals?
Then you got to do it for alpha too. 0 equals alpha colon alpha.
I wonder if we do.
0 equals omega colon alpha.
Oh yeah, alpha. Yeah, that's right. Yeah, colon alpha. Yeah.
Now switch it. 0 equals
Well,
alpha
I'm
colon
not,
omega.
I'm not sure we. Oh yeah, we do. You're right. Stop. You're right. Yeah, there's a better way of. There's a better. I'll tell you what. Let me copy the one in from the Dfns.
It's gonna.
That's the one. Oh, there's an additional thing in that it gives the absolute value in the case they're positive. But that's the and the point I didn't make. Sorry, the point I was getting around to and I didn't make. We use recursion so frequently that. Oops. What I had here was GCD. This would work. Okay, so this is the GCD algorithm, the correct way of. It doesn't use subtraction. It uses a slightly more powerful mechanism of residue. So it's doing a lot of those chunks. Euclid would probably, I think, did use subtraction. But if you've got a very small thing here, and a very large thing, you can take a whole bunch of them off to start with. That's the residue. That's
And the reason it works by only checking the zeros because you're switching the
you're
others.
switching each time, yeah. So it goes wrong. That's Now, what we can do here is to this recursion is used so frequently. Call myself. Call this thing that actually I'm in. That we have a special symbol, which is just del, and that means call the function that I'm in. And the nice thing about that is I can rename this function without having to go through and find any recursive calls in it. So that's the fully paid up Euclid's GCD. And of course, in Dyalog now there are primitive functions. GCD is primitive.
All around.
All around, yeah. All the V-shaped one. Yeah. Okay, so that's we're nearly there. That's. Yeah, that's okay. That's good. I suggest we go on to about 1:15 and then find some coffee and then take a break. Was that is that sort of shown up lots of stuff? Do we need to go into that a bit? You're probably surprised to think that that's all you need to write any. How would I write my payroll system armed with only a guard and a recursive call?
Do you have problems with the stack limit?
Okay, that's the sort of question I would have paid you to ask. There's a trick. Okay, there's a trick. Right. Let me write a function. Here's a function to add two natural numbers. Are, I think, non-negative whole numbers. So numbers like 0, 1, 2, 3, 4 up to whatever. And here's a function to add two natural numbers together. Okay, so let's call it the sum. Have I already got a sum? Ooh, that's not going to work. That's a session trick. If I want to erase something but I'm not quite sure what I'm erasing, edit it first and then just change the D into erase, so that you know what you're erasing the right thing.
Is it the same as quad-EX? Is it the same as quad-EX?
Yes, erase is the same as quad-EX. More visiting.
What do you have to do in a function?
Yeah.
Right-brain functions don't work inside the code.
Yeah, you can't put it. That's right. It's exactly that. And there's a subtle difference as well in that quad-EX. If you're suspended in functions, when you type quad-EX of a name, it looks down the stack to find the first one, and it hits that. It erases that one. Whereas paren-erase goes right to the bottom and erases a global name. Paren-erase doesn't erase local names in Dyalog. And that's for quote historical. All APLs used to work that way. And typically the system commands work only on global names. So paren copy, paren erase. What else? Paren funds, paren vars give you global names. They only look at global names. They ignore any localized names. I'm sure that's true of APL 2 and APL 360 before. Okay, so here's a function to add. There may be quicker ways of doing this. So what I can say here, what I'm going to do, I'm going to run it. When I run it, I'm going to say 3 sum 4, and I'm hoping to get a 7. And what I'm going to say here is if alpha equals 0, then omega. That's fair enough. If I add 0 to something, it doesn't hurt. Otherwise, I'm going to add alpha minus 1 recursively to omega plus 1. Okay. Or let me write this another way. 1 plus. Well, let's test it, and then if it works, I'll brag about it. If it doesn't, okay. So that seemed to work. Yeah. So let's put a trace in here. And let's test it. So again, the recursive thing is that what we can say here is that adding alpha to omega is one more than adding one less than alpha to omega. End of story. That's all you need to do. Don't whinge to me, go and see Mr. Piano. Is it Mr. Piano that told me that would work?
But you're relying on the condition in alpha is 0 and you return omega.
Yeah. Yeah. So if alpha is 0, the sum of alpha and omega is. This only works for now. Don't try this with floating point numbers and negative numbers. It only works with proper God-given numbers, not any of this nonsense. Yeah. So can you see? This is clearly there are better ways of adding numbers together in APM. Yeah. Can you see how this works? Yeah. And you can see it works. So 3 plus 4 is 1 more than 2 plus 4 is 1 more than 1 plus 4 is 1 more than 0 plus 4 and yeah. And I can run this on if I let's run this a little bit and look at my SI. What we can see here is let me go through again. So if I run this and look at the state indicator, then I've got one level of suspension and alpha and omega are 3 and 4. Alpha is not 0, so I'm going to call this recursively with alpha minus 1 and omega. So alpha and omega are this. And the state indicator looks like this, because it's calling. And now for NSI, and so on and so on. Now here the state indicator is about as deep as it's going to get. Alpha this time is 0, so the result alpha and omega. Okay, so I'll wipe back up. So actually I can probably show this a little bit better. Let's show you this. What I could say here is result is, and then return the result. Okay, that shouldn't change anything. But what it's going to do is to allow me to go in, and now that top one's popped out again, so the result here is 5, and then when I drop back a level, I'm adding 1 to that. I'll drop back a level, and then I'm out.
Do quote gets result.
Sorry?
Quote quad gets result.
Quad gets yeah, okay, that's good. Oh, that's a good idea, yeah, quad gets. Quad gets result. Yeah. And that last 7 was the one that popped out onto the session. So that's one we're doing. And of course, if I try to, that's fine, except if I were to try to add.
25 worked.
Oh no, it's the other way around. Yeah, that's going to. Well, we can't even see that decrementing. That's probably going to give me a wistful, and that's okay. But it would restrict the. That would cause some problem. Now there's a trick that all of the functional languages use. Let me just go back to the original definition. and I can code this in a slightly different way. And it should be the same. What I can say here is I can take that 1 plus and I can add it to here. So this is a different algorithm. What I'm saying is 3 plus 4 is the same as 2 plus 5. It's the same as 1 plus 6. It's the same as 0 plus 7. It's the same as 7. Ah! Stop. Okay, and if I put in the okay, 3 plus 7 is the same as 2 plus 8 is the same as 1 plus 9 is the same as 0 plus 10, which is 10. And the trick, this is an implementation trick, and it's called tail calling, and it's not, you shouldn't really be concerned about it. In many cases, in a Dfn, we say it's an expression preceded by the 0 or more local definitions. In many cases, the expression that we give on the last line is, if it involves a call on a function, a recursive call on a function, nothing else is done to that result on return. Effectively, this line just hands off responsibility to somebody else. It doesn't say return the result to me and then I'll fiddle around with it. It's just saying that's the result. And the trick is the interpreter is smart enough to realise that the result of this recursive call is actually the result of the line as a whole. And so it doesn't code a function call, it just codes a branch. So internally, this is implemented as a loop, and if I run this, what we'll see, if I go to the SI, is there's never more than one stack frame, because although this looks like a recursive call, the interpreter knows that it's never going to have to do anything but return the result. It just codes it as a jump with different alpha and omegas. And this is called tail calling, and it's, sorry, yes, Jim?
Is this also valid for for normal defined function?
No, and it's not, because it's really difficult to do with, it's more difficult to do with trad phones, because they don't have this simple, this is the expression as a result. In a trad phone, you have to name the result, and it can't tell easily whether you're then going to exit the function or what you're going to do next. Whereas, because this is such a simple syntax, in fact, the way this is, you don't need to know this, but what happens is, when the interpreter evaluates this, the way the Dyalog interpreter works is it evaluates the lines starting from the right, and it just plugs along to the left. So it picks up the 1, it picks up a plus, it finds the omega and adds those together as a right argument. Then it finds its recursive call, which is sum, and then it evaluates, before it can call it, it's got to evaluate the left argument. So it goes into these parentheses and evaluates the left argument, and then it's only when it gets here it can evaluate this, it can call the function. And then just as it calls this function, it says, where did I get to in the line? Is there anything to the left of that? No, there isn't. So I can code this as a jump rather than a recursive call. So it's safe to do. It takes a little while to get the hang of spotting these, but effectively, if this is, if you were to say result gets here, then when the interpreter evaluates this, it'll have the, see, I use gets instead of is. If that's the result is, then the interpreter would know that it's actually got to call this recursively and return a result. In that case, it won't do a tail call. It's a bit of a subtle thing you can play with. But it doesn't make any difference to the way that you code. But what you'll find is that if the interpreter, it's an optimization that the interpreter uses, and it avoids wistfuls and stuff. That's called tail calling. Some people call it tail recursion, but it's slightly more general than that. If a dfn is calling other dfns within the same block, then it will use the same techniques as well.